Welcome to the Math Record. Today we'll be learning about implicit differentiation. This video will cover part 4 of chapter 2 in our calculus class. Okay, let's begin. What is implicit differentiation? So implicit differentiation. Okay. F also. Sorry about that. Okay. And basically, implicit differentiation is another word for just basically finding a derivative. So differentiation is just another word for basically derivative. So, but instead of finding a derivative with one variable, now you have two. So what does that basically mean? So implicit differentiation, we have let's take for example an equation of a circle. So we have x squared plus y squared is equal to 25, right? So let's take this example of a circle. So how will you take the derivative of this? The usual case is that you want to have y into one side, right? So usually let's just say you want to minus x squared, so then you have y squared is equal to 25 minus x squared, and then you square root both sides, so you get y is equal to square root 25 minus x squared, right? And then you take the derivative of y, so y derivative is equal to, you could rewrite this as the same thing as 25 minus x squared to the power of 1/2, right? You go, when you're doing a derivative of fraction exponents, you basically just still follow the same rules. You just need to follow the power rule for derivative rules, which we covered on chapter 2, part 2. So the power rule. So you just whatever you have for the exponent, just bring it down. So you have 1/2, so you just bring it down 1/2, right? So then you always subtract 1 from that exponent. So 1/2 minus 1 is just negative 1/2. So negative 1/2 would mean that the exponent has to be a reciprocal. So you have sorry, oops, okay, equals 25 minus x squared to the power of 1/2, right? That's under the fraction. Because this would be negative 1/2, you move this to the top. So this would be 1/2 times 25 minus x squared to the power of negative 1/2, which is basically the derivative of this. But that's not all. You have this inside, which you need to chain, because usually it's just x to the power of 1/2, right? But now you have 25 minus x squared into x. So you have to chain that inside. So when you chain that inside, you have 25 minus x squared. That is, the derivative is just negative 2x, right? Because this is just another power. So derivative of 25 is 0. Derivative of negative x squared is just negative 2x. So adding them together, because it's just because they're basically two equations. So we just use the derivative rule for addition, basically. So we split up into parts of 25 and then 25 and negative x squared, which is just, this is 0, so negative 2x, and then you have negative 2x left over. So let's just write that down. And then we can simplify this. So the 2 here cancel out with this 2, so all we have left is y. The derivative of y is equal to negative x all over, we would just write this as a square root again, so 1/2 is just square root. Is square root 25 minus x squared. So the derivative of y is equal to negative x all over 25 minus x squared. You could leave it like this, but you could also substitute this part of the equation with this. Because you already know that y is equal to square root 25 minus x squared. Sorry if it's messy right now, but basically the idea is that you want to get it back to really simple variables. So you have negative, so the derivative of y is also the same thing as negative x. Let me rewrite this kind of a little bit neater. Equal to negative x all over y, right? This is the same idea because square root 25 minus x squared is just y. So you see how much work we did just so we could get the derivative of y for a circle. Instead of doing all this, we actually try something called implicit differentiation. So let's reverse this. So delete. and we get, okay, so the implicit differentiation is if we have x squared plus y squared equal to 25. Implicit differentiation is that if you have two variables on one side, basically. Even if you could like take one out, you could always do implicit differentiation if you have two variables on one side. So we have an x and we have a y, so that's two variables. So it basically satisfies that condition. So that's all we need to know. So basically, when we're doing implicit differentiation, what you're usually doing is that you're doing a derivative in respect to basically only one variable, and usually it's the respect to the x. So, or if you're doing something with time, it's just respect to time. So how it works is really simple. So basically, we're gonna split this up into parts. So we're gonna do the derivative of this first, then the derivative of this, and then the derivative of this. Okay. So the derivative of the left side, so the x squared plus y squared. So the derivative of x squared is basically just 2x, right? It's basically just that simple. Because usually when they do implicit differentiation, I usually use apostrophes, right? So this apostrophe for derivatives. Another way that I shown before is that you could use d over dx, right? So I could prove it with using d over dx. So how it usually works is that we could split this up into parts. So if we do the derivative of this side and the derivative of this side, right? We'll say d of dx of x squared plus y squared is equal to d of dx of 25. It's the same notation, basically. Instead of using apostrophe, we're using d of dx. So the derivative of this equation in respect to x. So basically, we can split this up into parts. So d of dx of x squared plus d of dx of y squared is equal to d of dx of 25, right? So we split this left side into parts. So whenever you do this is that you do the derivative first and then you do any canceling later. So basically the derivative of 2 of 2x is a derivative of x squared is just 2x, right? So whenever you do a derivative in respect to x, you just leave it. So you don't have anything to cancel. So if this is x to the power 3, we just have 3x squared. So just leave it like that. Just leave it at 3x squared. So anything with the x, whatever you're doing with the same variable, so you're doing respect to x and you're doing x, basically just leave it as whatever you have. And then you plus, because you have this plus sign, right? And then the derivative of y. So we have different variables here. We have x and y. So then you when this happens, you leave a derivative, one derivative, only one of basically the variable that you're doing. So of y, not x, of y. So the derivative of y squared, we just use the basically the same derivative rules. So we move, since it's an exponent, so it's y to the power of 2, we move exponent down, which is 2, and the variable is y. So 2 minus 1 is 1, but you just leave it as this. So this is the same thing, because it's just x squared and this y squared. They're the same thing, it's just different variables. But now for this case, what we have left is that we have a dy over dx left, basically, because because we're not doing it in respect to what we're not doing the derivative of y in respect to y. We're doing the derivative of y in respect to x, right? Of this x. So you cannot cancel each other out, because for this side we did the respect of derivative of x in respect to x. So this kind of just cancel each other out because they're the same thing. But you can't cancel this out. So whenever you do like a derivative of any like variable that's not the same thing as what you're doing the derivative in respect to, then basically you're just gonna have to multiply by a derivative of that variable. So it'll be 2x plus 2y. That 2y is multiplied by the derivative of y. And it's only a single derivative. So even if it's something like y to the cube and you're doing the derivative of that, it's 3y squared times the derivative of y. It basically is just simple. So if you just see anything that's not what you're doing the respect to, just do just multiply whatever you have left, whatever you have by by a single derivative of that variable. And the right side, the derivative of 25, derivative of any number is just basically 0. So unless it's like it has to be a function for it to be a to actually leave anything. So if it's like just a number like 1, 2, 3, 4, -1, 0, like 5, it's basically just 0. So we just have this. So we have 2x plus 2y is the derivative of y. So you see how we do it? Now we just need to isolate y. So we could just subtract 2x to a different side. So let's move this up. Okay. So we just have 2y times y, derivative of y. Subtract 2x to both sides, so that's minus 2x. So the derivative of y is equal to negative 2y. Divide by 2y on both sides, so you get 2y. And now you get derivative of x over y, which is what we did when we did like minus x squared and square root that, like the first method we did, which is the same outcome. But this is, even though it looks slower, if you get really good at it, it's really, really simple. And you don't even have to use d of dx. So it's basically this simple. So so the usual way of how I would do it is that like we have x squared plus y squared. So instead of doing like the 25 minus x squared and then like square root that, the first method, or like doing the second method with d of dx, usually how I do is that I do the derivative of the first part, which is 2x, right? And then I add, because the symbol is add, and then the derivative of y squared is just 2y, right? And then you just, whatever you have left, you just multiply by the derivative of that variable, so it's the derivative of y, and then derivative of the number is 0. And then basically you minus 2x, so 2y times the derivative of y is equal to negative 2x. And then divide by 2y from both sides, so you get negative 2x divided by 2y. So you get negative x over y. See, it's basically just that fast. So if you understand how to implicit differentiation works, it's not even really that difficult. Basically, what you have left is just multiply the derivative of y. So you're multiplying. If you're doing a derivative in respect to whatever you're looking for, it's x. Basically, it's always x. Usually, if you have multiple variables, it's just x. So you have x and y, it's just x. And if you're doing time versus like height, then it's just basically time. You're doing respect to time. So basically, this is how it works. You just need to understand whatever you're doing your respect to is whatever you is on your x-axis. So your x value is on your x-axis, right? Your time is on your x-axis. So you're doing respect to time, you're doing respect to x. And that's how I remember it. And then whatever you're not doing respect to, basically you just multiply that variable. Like how I did with y squared is derivative of y. You have to multiply it. So it's basically just that simple. And it's always just a single y, the derivative of y. It's not like derivative of y squared or something. So it's basically that simple. And then you just basically just put all the derivative of these y together, and then you kind of just get the derivative of y. Sometimes it's not really that simple, and you can't like subtract x squared and square root y, right? Because in this example, you could, but for implicit differentiation to have any value, it basically is that you can't find a derivative with like even like factoring some things out, like with the x. Like we can't separate the x and y. So let's try an example with that. So we'll try a case where only like implicit differentiation works, because there's two cases. There's implicit differentiation and there's explicit differentiation. Explicit differentiation is what we've been using a lot. Implicit is what we're using now, which is with two variables and you can't factor it out, and you can't like you have two variables, you can't factor it, and you can't like arrange them in the way that you could like take separate one from the other. So let's try a case like x to the power of, let's write this a little higher so we get more room. X to the power of 3, right? Plus x times y plus y to the power of 3 is equal to 20. And let's say we want to find the derivative at like x is equal to 2, right? So basically, the first thing you want to do is that you want to find the derivative of this, or you want to or you want to find y. Because usually it's one or the other. It doesn't matter which way you do it. I usually like to I usually like to find the derivative first, because then I could just plug it in later and then do it. It doesn't matter. Either way is fine. So the derivative of 3x squared, right? Because you're just adding, so you just do a derivative by addition, the addition rule. So x to the power of 3, bring the exponent down and then subtract 1 from the exponent. So the derivative of x cubed is just 3x squared. And you plus, okay, so you x times y. So you have to use the product rule because you're multiplying like numbers, values together. So basically, the product rule is the derivative of the first one times the normal of the second plus the normal of the first times the derivative of the second, right? So the derivative of x is just 1, and then multiply by y. And then we have x, right? And then derivative of y is basically just 1, right? But derivative of y is 1, but so you don't have to multiply by anything. But then, as I always say, when you ever do a derivative of a value, you're not doing your in respect to, basically, then you always have to leave the derivative of that value of that variable, which is y. So you just leave a derivative of y. Basically, that's just that simple. So y to the power of 3, right? So you just drop down the 3 from the exponent. You have y squared, and then you always leave a derivative of y if you're not doing to the x, basically. So then the derivative of 20 is 0. So the derivative of this top equation is basically just this. It's basically just that simple. Okay, so now let's just put like the derivatives of y together. So you have a derivative of y here, you have a derivative of y here. So let's move everything else to the other side, right? So we have x times the derivative of y. So we have this one. And now we have to have this one now, which is 3 times y squared times the derivative of y. And then we just move this and this to the other side. So we have minus 3x squared, and then minus y, right? Because that's just 1. So yeah, minus y. So this is equivalent. So factor out the the derivative of y. So you have derivative of y, x plus 3y squared is equal to negative 3x squared minus y. So the derivative of y is equal to negative 3x squared minus y divided by x plus 3y squared. You see how weird this is like something that we get like kind of simple like this, right? Somewhat simple. It still looks kind of difficult. We have this kind of derivative which uses x and y together. So usually when you do derivatives, you only have one variable, like usually just the x. But now when you have implicit differentiation, you usually have two variables. So you have x and y. And that's why you can't really use explicit differentiation, because you can't separate out x squared, like x and y, this x and y together from like these variables. So even if you minus like y cubed this side, right? Like there's no way for you to take out like this y. Like you could distribute out the x like 1x, but you still have a y left over. There's nothing you could do. So when you have something like this, you have to use implicit differentiation. So if you want to find the derivative at x is equal to 2, right, you need a y value, right? So all you need to do is that, like that's why I said it doesn't matter which way you do it. You could plug in 2 into this equation, and then you get the y, or you could just do the derivative and then you plug in later. It doesn't matter. You're still going to get the y either way. So basically plugging in 2, so you have 2 to the power of 3 is 8, plus 2y, and then plus y cubed is equal to 20. So we have we need to find a value for y that works when it's 20. So we have 2y plus y cubed. 20 minus 18, 20 minus 8 is 12, okay? So usually I like to test points. You could use your calculator, but if you want to do it by hand, basically just test points. So the first point I usually test is like 0. 0 doesn't work, obviously. So the next point I would check is 1. So 1, that's 2, plus 1, that's 3. Okay, that doesn't work. So since I know 3 is less than 12, I would just keep going higher. So let's say 2. And that's 2 times 2 is 4. 2 to the power of 3 is 8. So 4 plus 8 is 12, okay? So the for y is 2. Use your calculator. Usually you will like to use your calculator because you sometimes get decimals. So it's really ugly numbers. So your x value is 2 and your y value is 2. Also 2. So you just need to plug them in to find the value. So negative 3 x squared, x is 2, so that's 4, so then that's negative 12. And then y is 2, so that's minus 2. X is 2, y is also 2, so 3, y squared is 4, so 4 times 3 is 12 also. So this will come out to negative 14, and this is 14. So the slope at 2, x is equal to 2, it's just -1. It's basically just that simple. So that's how you do implicit differentiation. So that's one example. Now let's try like another example so we get more familiar with it. So let's say we have x to the power of 4 divided by y plus like x to the power of 3 times y squared plus like y to the power of 5, right? And let's say we have equal to 5y. Let's actually not do derivative of this. This seems kind of ugly. So let's just try like implicit differentiation and get the general like answer. So we don't have to plug in like x or x into here and then get like a y. So, but if you want to like try like different numbers and see how the slope works, go ahead if you want. So let's actually try this. So we split this up into parts because I see the plus sign. So we do a derivative of this, then this, then this, and then this, basically. So the derivative of this part, since it's a quotient, it's x to the power of 4 divided by y. So we have to use the quotient rule. So basically, the derivative of the top portion, 4x to the power of 3, right? Multiplied by the normal equation of the bottom, which is y, minus the normal equation of the top portion, which is x to the power of 4, times the derivative of y. The derivative of y is just 1, but since we're doing a derivative of y, you have to leave a derivative of y, and then divided by y. So y squared, right? Whatever you have in your denominator, just leave a square of that. That's the quotient rule, basically the definition of it. And then you plus, so now we're going to do this portion now, which is x cubed plus times y squared, which is really ugly. So basically, which is just the product rule, but it's a lot of these is really ugly. Only this one and this one actually. So y to the power of 5 is fine. Y to the power of y, 5 times y is also fine. So this portion is the same thing as saying the first equation, which is x to the power of 3. So the derivative of that is 3x squared times the normal equation of the other one, which is y squared. If you're not doing the derivative of it, you don't have to times y, times the derivative of y. Only when you're doing the derivative of it, you have to do the derivative of y, multiplied by the derivative of y. But if you're not, then you don't have to. Okay, multiply by y squared, right? So you don't have to multiply by derivative of y, because you're not taking the derivative of y squared at this point. And then you have x cubed. Now you want to take the derivative of y. So the derivative of this of y to the power of 2 is 2y. And when you're doing the derivative of y, because you're doing respect to x, you have to leave a derivative of y. Okay, oops. Okay, we have to leave a derivative of y. And to keep going, because now we're doing this term. This one's pretty simple. It's just derivative of y to the power of 5. It's just 5 times, bring the exponent down, which is 5. Subtract 1 from the exponent is 4. And then you have to multiply by a derivative of y. And all of this equals to this one, which is 5y. So the derivative of 5y is just 5, and then you leave a derivative of y, right? So basically, you just want to put all the derivatives of y together. So you have one here, you have one here, you have one here, and you have one here, okay? So this seems like a whole mess. So let's kind of move this up a bit so then we get a little bit more room. Okay, so we have this. So let's just, whatever we have, let's just, whatever like derivative of y, we'll just move it to the side, okay? So then we'll keep track of everything. So then we have 4x cubed to the power of y divided by y squared, right? What else do we not have with the derivative of y? We have this one right here, okay? So there's no derivative of y here. So we have plus 3x squared, y squared. So usually I like to cancel out what I already used. So I already used this portion, I already used this portion. Everything else seems to have derivative of y, okay? So we would just get that to the other side. So we have y, derivative of y. Actually, let's just distribute out that first. So we have y, 5, right? So we have minus here, so you want to get to the other side. So minus and minus is just positive. So this one would be plus x to the power 4 divided by, because you have a y on the bottom, so you have y squared. So we distribute out the y, so this is checks. So you put in the y back in, so this 5y, 5 times the derivative of y, which is this portion, and then x to the power of 4 divided by y squared times the derivative of y is basically this portion right here. So we already have this portion out. So already done with this equation. We're done with this one, and we need this one. So we have x cubed times 2y, so plus x cubed times 2y. We already distribute out the derivative y, so take that out. So you can do this on paper if you want. It's just that I'm kind of running out of room because I'm doing it on a online, writing this out. So sorry about that. It's really hard to write. And take out this one is just really simple: 5y to the power of 4, and close that parentheses. And now we're done. And then we have this left, right? So let's move it up so we get a little bit more room. Okay. So now we just need to divide all this to the other side. So then we just did the derivative y. So we have 4x cubed, right, from this side, divided by y squared, plus 3x squared, divided by y squared, all divided by this number, which is 5 plus x to the power of 4, divided by y squared, plus x to the power of 3, and that number was 2y, yes, 2y, plus 5y power of 4. Oops, we don't have a parentheses there. And this is all equal to the derivative of y. See, you see how complicated this would be if you even try to use for explicit differentiation. And this is why we use implicit differentiation, because we get really ugly like equations like these, and then we have to use implicit differentiation. And that's the idea of how to like basically do implicit differentiation. So basically, whenever you see anything with like one variable, or you could separate it into one variable, like how we did with the circle, then you could just use like for example, the circle, the regular polynomials, the trig functions, exponentials, like just the regular ones, like not really anything complicated. You could use the explicit differentiation. But if you see anything but like two variables and you can't factor them, then you have to use implicit differentiation, which is not all too difficult because, as I said, you basically just do the derivative of anything that's, if it only has x, then you just do anything with normal with x, how you do with regular derivatives. And then when you see anything with y, basically you just add a you just multiply whatever you have by the derivative of y. So it's basically just that simple. And that basically covers everything for implicit differentiation. Thanks for watching, and I'll see you at the next math record.